Good morning, students. Today we are going to talk about 14 group elements. Group 14 elements are 40 group elements. So this 14 group elements, they have the elements carbon, silicon, germanium, tin, lead. And here in this group we are going to discuss mainly about the first two elements, that is carbon and silicon. So the chemistry of carbon and silicon, here we are going to discuss in 14 group elements. Now let's see the general characteristics of these elements. First one is occurrence, that is where do they occur. So all these elements, they occur in the combined state, that is in the pure form. They do not exist, they exist in the combined form. Allotropes of carbon, that is diamond and graphite, are largely available in the elements form only. Uh, and we also know that activated charcoal and gas carbon are very readily prepared in the laboratory. Next, second element about silicon. Silicon is the second most abundant element in element by weight. Tin and lead are well known since before biblical times. But germanium is very rare. It occurs together with the zinc and silver minerals. So combined state they exist, we said. And 14th group elements occur as oxo compounds, that is oxides. We know this is SiO2 silica, a very much common compound. And this is SnO2 tin oxide, and uh, carbonates, that is carbon is available in the form of carbonates like calcium carbonate and sulfates. Lead, it exists in the form of a sulfate, lead sulfate. So this is about the existence or occurrence of these elements in the earth's crust. Next, let's study about the electronic configuration. And these elements, they have 4 electrons in the valence shell, therefore their outer electronic configuration is ns2 np2, that is 2 electrons are present in the outer shell of s orbital and 2 electrons are present in the outer shell of the p orbital. So here the general valence configuration of these elements is ns2 np2. And in the case of these elements, the inner core of electron configuration of elements of this group also differ because of the appearance of d and f orbitals. So in the case of all the elements, let us see this configuration, then we will come to know what is meant by that. So here if we consider carbon, the symbol is C, and atomic number is 6. Here we can see the electronic configuration of carbon, that is helium 1s2 2p2. Helium, that is 1s2 and 2s2 and 2p2, that is altogether 6 electrons. Here 2 electrons, here 2 electrons, 2 electrons, altogether 6 electrons are arranged like this. So here the outer configuration we can see ns2 np2. And if we consider the second element, that's a silicon, its symbol is Si and atomic number is 14. Electronic configuration, if you consider, this is neon, that is 10 atomic number, 3s2 3p2, that is 10 plus 2 plus 2, that is 14 electrons. Here also ns2 np2 we can come across. Let's consider the next element, germanium. Symbol is Ge, atomic number is 32, electronic configuration argon 3d10 4s2 4p2. So here d10 electrons we come across. Argon is 18 and here 10 electrons 28, 30 and 32. So here outer electronic configuration is same, ns2 np2 here also. But inner core, here d electrons are present. Here d electrons are present. In the case of this last element, that is lead, here we come across f electrons as well as d electrons. So this is inner core of electronic configuration that differs in the case of these elements, we said. So first two elements, ns2 np2, d and f electrons are not there. But here as we move down, as the atomic number increases, we can also come across d and f electrons. So then if we consider atomic number is 50 and symbol given is Sn. Then here the electronic configuration, krypton 4d10 5s2 5p2. Krypton is 36 plus 10 is 46, 48 and 50. Okay, so let's, if we consider, this is plumbum, this is stannum, this is plumbum, Pb symbol, and the atomic number is 82, and its electronic configuration comes out to be xenon for F14 5d10 6s2 6p2. That is, xenon is 54, here 14 electrons, 68 plus 10 78 80 and 82. So this is about the electronic configuration of 14th group elements. Now let's see the oxidation states. So these elements, they have 4 electrons in the outer shell. If they use all the 4 electrons, they exhibit plus 4 oxidation state. If they use only this np2 electrons in the bonding, they exhibit plus 2 oxidation state. So the electronic configuration of this group elements is, the outer configuration is ns2 np2, therefore they exhibit plus 2 and plus 4 oxidation states as common oxidation state, whereas higher elements, that is heavier elements, if we consider of this group, they exhibit only plus 2 oxidation state is the common or most stable oxidation state of heavier elements like lead due to inert pair effect. Inert pair effect, that is non-participation of S electron pair, that is ns2 electrons of the valence shell in the bond formation. So that is known as inert pair effect. So because of this inert pair effect, the heavier element like lead, it exhibits plus 2 oxidation state as stable oxidation state than plus 4. And carbon and silicon, they do not exhibit plus 2 oxidation states in their stable compounds. Okay, in the carbon family, the stability of plus 2 oxidation state gradually increases as we move down the group, and ultimately reaches maximum stability in the case of lead compounds. And this is due to inert pair effect, as we discussed. SN2 ion exists normally, that is tin. This is stannous ion, Sn plus 2 ion. It exists normally, but it is a strong reductant. Reductant, that is reducing agent. Reducing agent in the sense which undergoes oxidation. Which undergoes oxidation, that is known as reducing agent. Oxidation in the sense it has the capacity to lose the electrons, so it can easily promote its electrons. Then Sn plus 4 ion forms compounds with greater covalent character. So Sn plus 2, if it loses 2 electrons, it becomes Sn plus 4, as it is acting as a reducing agent. That is, it gives electrons to other substance and it undergoes oxidation. That is called reducing agent. So then Sn plus 4 ion is formed, and which has more or higher grade covalent character, greater or higher covalent character. In Pb plus 2 ion, the energy for promoting the electrons is higher. Because of that reason, this is more stable in plus 2 oxidation state than in plus 4 oxidation state. Next one is atomic and ionic radii. That is, the atomic radii increases down the group. In any group, same thing happens due to increase in atomic number. Due to increase in orbit number or atomic number. The difference in radius of silicon to germanium is less due to d block contraction, and between tin and lead it is due to lanthanide contraction. So gradually atomic radii increases down the group, but the silicon to germanium, the increase is less due to d block contraction, whereas from tin to lead the increase is less. This is due to lanthanide contraction. And the atomic radii of this group elements are smaller than atomic radii of 13 group elements. So from 13 to 17 group, gradually, we know across the periodic table, the atomic radii decreases. Therefore, the atomic radii of this 14 group elements is less or smaller when compared to atomic radii of 13 group elements. Next one is ionization enthalpy or ionization energy. This is another general character of these elements. Now, if we consider the ionization enthalpies of these elements, generally as we move down the group, what happens to ionization energy? In any group, As we move down the group, ionization energy decreases due to increase in atomic size. Due to increase in atomic size, the ionization energy gradually decreases. And here also same thing happens, decreases down the group with increase in atomic radii. So first ionization energy of this group is more than the comparing members of 13 group. Yeah, generally ionization energy across the period it increases. Therefore, 14 group elements they will be having higher ionization energies when compared to 13 group elements. And small decrease in first ionization energy from silicon to germanium and slighter increase in ionization energy from tin to lead is the consequence of poor Stirling effect of intervening d and f orbitals. So as we move down the group, what happens? Ionization energy decreases, we said, but here silicon to germanium, there is a slight increase, and from tin to lead, here sorry, silicon to germanium small decreases there, that is common, but it is less, decreases there but it is less. But of tin to lead there is increase, slight increase in ionization energy. This is due to poor Stirling effect of uh, the d and f orbitals which are present in between the nucleus and the outer shell. Next one is electronegativity. Electronegativity in any group generally decreases down the group due to increase in atomic size and the screening effect of inertials. So here also same thing happens, and carbon has its maximum electronegativity and lead has minimum value of electronegativity. As move down the group, electronegativity decreases. Carbon electronegativity is 2.5. So that we should. Next one is catenation property. This is the special property of fourth group elements, catenation property. So here, what is meant by catenation? Let us discuss. So catenation is nothing but it is the tendency of an element to form chains containing identical atoms, and sometimes rings also is known as catenation. So catenation is nothing but tendency of an element to form long chains and rings of identical atoms. So these chains may be straight chains or branched chains or cyclic chains. Okay, so catenation is not possible unless the element has two or more valences. Minimum two valences it should have, then only chains can be formed. And carbon is the most important of very few elements that show catenation in their chemical properties. Catenation is the special property of carbon, especially we can say, and that carbon is tetravalent. Because of this tetravalence, it can form long chains and rings very easily, and it can form single or multiple bonds with its own atoms. We know C double bond C, C triple bond C. So it can C single bond C. So it can form single bonds and multiple bonds, that is double and triple bonds with its own atoms. So silicon can form chains to some extent, but the catenation property of silicon is less when compared to carbon. And here we can see compounds of silicon are not as stable as those of carbon. And the high stability of carbon chains can be understood from the relative bond energies. So why this carbon? It is having high catenation power that we can uh, understand with the help of bond energies. Now let us see the bond energy of CC bond, SI bond, GE bond. CC bond energy is 348 kilojoules per mole, whereas that of silicon bond energy is 297. And as we move down the group, what is that happening? Bond energy is decreasing. So greater the bond energy, greater is the strength of the bond. So CC bond, it is stronger when compared to this bond, SI, and this is stronger when compared to this. This is stronger when compared to this here. No, such type of bond cannot be formed. From this, we can say that carbon-carbon bond is more stable, more strong, more stable. Therefore, its catenation power is more and it can form long chains and rings readily. Here we can say the order of catenation capacity of this group elements. Carbon is very much greater than, okay, very much greater than silicon, which is greater than germanium, which is equal to or greater than tin, which is greater than lead. So the bond energy, just now we have discussed, that is metal, element to element, let me say, because all are not metals. Element to element bond energy, M is 14th group element, okay, gradually decreases with an increase in atomic weight. So this we can explain that this order. This order can be explained with the help of the bond energies. Next, allotropy. Allotropy, the periodic table. Many non-metals, they exhibit allotropy, and to some extent some metals with different structures, they also exhibit allotropy. So now let us see the allotropy exhibited by carbon. So the allotropic forms of carbon are of two types. They are crystalline and amorphous. Crystalline carbon and amorphous carbon. So the important crystalline allotropes are diamond and graphite, we know. And nowadays fluorines are also added to diamond and graphite. So the crystalline allotropes of carbon are diamond, graphite and fluorines. And due to the difference in the arrangement of atoms and the bonding capacities, the diamond and graphite, they exhibit different physical and chemical characteristics. So, though they are crystalline allotropes, they will be having different um, chemical and physical properties due to difference in the arrangement of carbon atoms. Now, let's discuss the structure of diamond and graphite. First of all, let's talk about diamond. Diamond is the three-dimensional polymeric structure, and in diamond, carbon atom, it undergoes, you can see, sp3 hybridization. Okay, it utilizes all the sp3 hybrid orbitals, all the four sp3 hybrid orbitals to form sigma bonds, sigma bonds, carbon carbon sigma bonds. Therefore, each carbon assumes a tetrahedral symmetry due to sp3 hybridization. So we know here hybridization, it dictates the geometry of the molecule. As sp3 hybridization is present in diamond, the molecule should exhibit tetrahedral symmetry or tetrahedral structure. So then here each carbon atom, it is bonded to four other carbon atoms in tetrahedral symmetry. Due to this structure, diamond acquires extreme hardness. It is the hardest substance, we can say. So to melt diamond, the extremely stable CC bonds in it only must be broken, and there is no other way. So because of that reason, its melting point is very high. Its melting point is here, very high. Okay, this is melting point 3600 degrees centigrade. This is boiling point. So very high heat energy is required to break all the CC bonds. Therefore, the diamond has high melting and boiling points. See, no other element has such high melting point. Okay. Next, let's see the structures. Compared to diamond, the structure of graphite is different. Yes, we know this. In graphite, a layered lattice structure is present, whereas diamond, it has three-dimensional polymeric structure. And graphite, it has two-dimensional layer structure. See, this is diamond, three-dimensional polymeric structure, giant polymeric structure, whereas graphite has layered lattice structure. Many layers are present, and each layer contains such type of hexagonal rings. Okay, and this is nothing but fullerene. It's like football structure. It will be having five-membered rings and six-membered rings. Fullerene. Now, if we consider graphite, so this is about the structure of graphite. The forces between the layer lattice structure graphite has. The forces between the layers are weak van der Waals forces, and the distance between the adjacent layers is 3.35 angstrom units. As a result of the density of graphite is less because of this layered lattice structure. Density of graphite is less when compared to that of diamonds, and it is soft. This is also soft. Because of that reason only, graphite can also be used as a lubricant. So the cleavage of the layers also is easily done because of the difference in their structures. Diamond is used as abrasive, whereas graphite is used as a lubricant. So graphite, it is soft and slippery. Because of that reason, it is used as a lubricant, whereas diamond is very hard. Because of that reason, it is used as abrasive. Now in graphite, each carbon it utilizes three valence shell orbitals, that is, it undergoes sp2 hybridization, and as a result it forms three hybrid orbitals are produced, and which form three sigma bonds with the other three carbon atoms. And the remaining fourth anhybrid orbital, it has an unpaired electron which forms a pi bond with other carbons by lateral overlap. And these pi electrons behave as a group of free electrons due to resonance. Because of this reason, this graphite, it has the ability to conduct heat and electricity. And these properties are contrary to those exhibited by diamond, because in diamond no free electron is present. Because of that reason, diamond does not conduct heat and electricity, whereas graphite does. And and because of this, graphite, it also has metallic luster due to the presence of this free electrons. Okay, next, diamond and graphite. If we see the few differences, our comparative study, graphite is relatively more stable. Because of that, it is very difficult to convert graphite into diamond, and it may be possible only at 3000 degrees centigrade. On heating the graphite to 3000 degrees centigrade only, it becomes diamond, because it is more stable. And high pressure is also, see the pressure, nearly 1 million atmosphere, nearly 1 million atmosphere pressure. This is high pressure we should apply, then only it will be converted to diamonds. And in diamond, single bonds are present in between carbon and carbon atoms. And to break these single bonds, it is very difficult. It's very difficult, and the bond energy is very high. And polymer chains are present in three-dimensional giant molecule. We said that in diamond it has three-dimensional giant polymeric structure. To break all these bonds, it is very difficult. And the chemical reactivity of diamond is very much less because of this chemical. It is inert because of this strong bonds. But graphite, it reacts with highly reactive sodium and potassium elements and gives brass colored compounds, because it is a little bit more reactive when compared to diamonds. And concentrated HNO3, HClO4, these are all strong oxidizing agents. They give graphite, they react with graphite to give graphitic oxide on reaction. Okay, so graphitic oxide is produced when concentrated nitric acid and perchloric acid, which are strong oxidizing agents, they convert graphite to graphitic oxide. And amorphous varieties of carbon, charcoal, carbon black, lamp black, animal charcoal, wood charcoal, these are all the different amorphous varieties of carbon. Next, let's see the next property, that is reactivity. Reactivity. So reactivity with water. Here, these are the elements: carbon, silicon, germanium, tin. They have no reaction with water. They are unaffected by water. Okay. Whereas this tin, it decomposes steam to form metal oxide and liberates hydrogen gas. Tin plus 2H2O gives rise to SnO2, tin oxide plus H2 gas. H2 gas is liberated when this tin, it decomposes steam. Okay. Whereas the rest of the elements, that is carbon, silicon, germanium, lead, they are unaffected by water. They have no reaction with water. Next reaction is reactivity with the oxygen. Oxygen. So when these elements are heated with oxygen, what happens? Let us see. When heated with oxygen, all elements of this group, they form two types of oxide. They mainly form two types of oxide. One is monoxide, the other one is dioxide. So here, if we consider carbon, carbon dioxide, this is carbon dioxide, this is silicon dioxide, germanium dioxide, these are the dioxides. So dioxides are acidic in nature, whereas these dioxide, that is carbon, silicon, germanium dioxides, are acidic in nature, and we know that non-metals, they form acidic oxides. The oxides of non-metals are acidic in nature. So carbon is a non-metal, silicon is a non-metal. So thus here uh, acidic oxides are produced, and whereas tin and lead, they have metallic character, therefore their oxides are basic in nature. And to some extent they also exhibit what is that certain amount of metallic non-metallic character also. Because of that reason, their oxides may be amphoteric in nature, maybe amphoteric in nature. So tin and lead oxides, they are amphoteric in nature due to metallic and non-metallic property of these elements. Mostly we can say that lead is a metal, but to some extent it behaves as a non-metal, therefore its oxide may be having this amphoteric nature, that is acidic as well as basic nature. And if we consider the monoxide of carbon, that is carbon monoxide, which is neutral, and this monoxide of germanium is acidic, tin and lead monoxides are amphoteric in nature. So this is about oxides. Next property is action with halogens, reactivity of these elements with halogens. All these elements, they form halides of the formula mx2 and mx4. mx2, yeah, where M stands for fourth group element, X is a halogen, that is fluorine, chlorine, bromine, and iodine. So elements react directly with halogens under suitable conditions to form halides, except carbon. Except carbon, the rest of the elements, they form the halides when they directly combine with halogens. The central metal atom in these halides undergoes sp3 hybridization. sp3 hybridization in mx4 type of halides to give tetrahedral shape, with exception to S and F4, PbF4, which are ionic in nature. So as we move down the group, metallic nature increases and their electronegativity decreases. Therefore, they combine with more electronegative elements to form ionic compounds. So here SnF4 and PbF4, they are uh, ionic in nature due to more electronegativity difference between this metal and these halogen atoms. Next, let's discuss about the compounds of carbon. There, the first one is carbides. First compound of carbon, about carbides. So, carbon is a versatile element that it can form compounds with elements having lesser as well as greater electronegative elements than itself. So, carbon combines with elements of lesser electronegativity and elements of higher electronegativity than itself. So because of that reason, it has the ability to form versatile compounds. So compounds of carbon with more electropositive elements are called carbides. So the compounds of carbon with more electropositive elements. That is, the other element should have more electropositivity than carbon. Then the compound formed is known as carbide. Now let us see. So on the basis of the bonding involved in these carbides, carbides are classified into three types. Ionic or electrovalent carbides, first one. Second one is covalent carbides, and third one is metallic or interstitial carbides. Metallic or interstitial carbides. So ionic or electrovalent carbides, first one. Second one covalent carbides. Third one is metallic or interstitial carbides. Now first of all, let's discuss about ionic carbides. Ionic carbides. So ionic carbides are also known as electrovalent carbides, we said, that is which are salt-like carbides. And how they are formed, let's see, they are formed by the metals of groups 1, 2 and 13. So carbon and metals of first group, metals of second group and metals of 13 group, except boron. 13 group. Boron is the first element of 13 group, which is a non-metal. So except boron, here first group elements, anyhow, first A group elements are all metals and second A group elements are also metals. This is alkali metals, alkaline earth metals, and in 13 group aluminium, mm, the rest of the metals present in the 13th group, they combine with carbon to form ionic carbides. Ionic carbides. And let's see how they are prepared. They are prepared by heating the metals or oxides or hydroxides with carbon. So these metal oxides or hydroxides, when they are heated with the carbon, are a source of carbon. Directly with carbon or with a source of carbon such as carbon monoxide or carbon dioxide, an aliphatic or an aromatic hydrocarbons, then we get the carbides. So carbides are obtained by heating the metals or oxides or hydroxides, metal oxide or metal hydroxides with directly with carbon or with sources of carbon such as carbon monoxide, carbon dioxide, or aliphatic or aromatic hydrocarbons. So then these carbides, ionic carbides, are produced. These ionic carbides, they form transparent colorless crystals. They are transparent colorless crystals with ionic lattices containing metal cations in the interstices between the carbon anions. So metal cations are present in the interstices between the carbon anions. So we will see the structure, then we will come to know what is that interstices. So these are all easily decomposed by water or acids with the formation of aliphatic hydrocarbons. So the ionic carbides, when they are decomposed by water or acids, then what happens? Aliphatic hydrocarbons are produced. So ionic or electrovalent carbides are further classified into different types. What are they? Let us see. First one, acetylides. Second one methanides, and third one allylides. So first of all, let us discuss about acetylides. So acetylides are the carbides which yield acetylene on hydrolysis. So these are the carbides, ionic carbides only, which yield acetylene, that is, which produce acetylene on hydrolysis. Then they are known as acetylides. So generally these acetylides are said to have C2 minus 2 groups. So any compound which has C2, C double bond C, 2 minus, okay, C2 minus 2 groups, when they are present in the acetylide, it produces acetylene when it is subjected to hydrolysis. Now here let us see the example. This is the best example, that is calcium carbide, which is an acetylide, which when subjected to hydrolysis, it produces acetylene. C2H2 is acetylene. So calcium carbide on hydrolysis produces calcium hydroxide and acetylene gas. Okay. So, as it is producing acetylene on hydrolysis, it is said to be acetylide. It is called acetylide. So, this is about the acetylide, which is an ionic carbide. And this type of carbides may be regarded as derivatives of acetylene, and thus they are known as acetylides. Okay. Next, let's see how these compounds have the structure. So, these are the ionic carbides. They possess a face-centered tetragonal space lattice with 4 molecules of Rc2, where R is the metal, calcium, strontium, barium, second group elements, alkaline earth metals, okay, in the unit cell. And this arrangement of atoms is present in deformed lattice of sodium chloride or zinc sulfide. This is about the lattice structures of these ionic carbides. So alkali metals and copper, silver, gold, they form M2C2 type of the compounds, and alkaline earth metals, that is calcium, strontium, barium, etc. Zinc and cadmium also. These are the second B group elements. They give MC2 type of carbides. MC2, that is CaC2 type. Okay, example CaC2, MC2 type of carbides. So first group elements they form M2C2 type of the carbides, whereas second group elements they form MC2 లేదా RC2 type of carbides. And 13th group elements, if we consider, they form M2C6 type of the carbides. M2C6 type of the carbides. And these are the structures of MC2 or RC2 type of the carbides. And second type of the ionic carbides are called methanides. Methanides. Okay, so methanides they yield methane on hydrolysis. Methanides are the carbides which produce methane on hydrolysis. Example is beryllium carbide. So here Be2C, beryllium carbide, aluminium carbide, Al4C3, aluminium carbide. So these carbides are called methanides because they produce methane on hydrolysis. These are hydrolysis reactions of beryllium carbide and aluminium carbide. On hydrolysis, they produce methane. Therefore, they are called methanides. So methanides are regarded as they are considered as derivatives of methane, and they said to contain C minus 4, the C minus 4 groups. So beryllium carbide Be2C. So beryllium double bond C double bond Be. Be double bond. One pair is one single bond, another pair another bond. C double bond Be. And aluminium carbide Al4C3. This contains such type of the structure. 4 aluminium and 3 carbons. Al4C3. Aluminium is third group element. It forms 3 bonds. And carbon is fourth group element. It forms 4 bonds. So this is the structure of Al4C3. And the next type of ionic carbides are allylides. Allylides. So allylides are the ionic carbides which yield or which produce allyline on hydrolysis. Allyline on hydrolysis. So the best example, the only example of allylide is magnesium carbide. Magnesium carbide. So magnesium carbide is Mg2C3. Mg2C3. So it has C3 4 minus ion. C3 4 minus ion or group. You can see here. This is ionic. So plus 2 here, minus 4 here. M2 magnesium ions. Therefore plus 2 into 2 is plus 4 and here 4 minus. So Mg2C3. Mg2C3. So when this undergoes hydrolysis, it produces allyline, that is C3H4. C3H4 is allyline. CH2 double bond C double bond CH2. That is allyline C3H4. So these are the three. First ionic carbide is acetylide, second one is methanides, third one is allylides, and fourth one is mixed carbides. Mixed carbides, fourth ionic carbides. So they yield a mixture of hydrocarbons and hydrolysis. Because of that reason, they are called mixed carbides. So the carbides of iron group and uranium, that is U2C3, belong to this type of carbides. And these carbides are related in structure of intermetallic compounds. Intermetallic compounds. Now here if we consider intermetallic compounds, in the sense they have the crystal structure like that of metals. Metals. Okay. Here if we consider calcium carbide, this it has such type of structure, and this is thorium carbide. It has such type of crystal structure. And next, let's see the reactivity of these carbides. Alkaline earth metal carbides are decomposed by dilute acids or water to yield acetylene gas. We have just now studied calcium carbide. This is acetylite, which hydrolyzes to form acetylene. Okay, they combine with nitrogen when heated in it. So these this is one reaction. On hydrolysis, they produce acetylene. Second one is when these alkaline earth metal carbides, they heated in presence of nitrogen, they combine with nitrogen on heating. So if it is heated with nitrogen, we get calcium cyanide, CaCN2 plus C. Now let's see beryllium carbide. It is a brick red colored compound, and it is hard enough to scratch glass and quartz. So quartz is one of the allotropes of silica, and it has very hard so that it is able to scratch glass and quartz, and they are able to reduce magnesium oxide to magnesium. So these carbides, they have the capacity to reduce metallic oxide like magnesium oxide to magnesium. So the carbides, they act as a reducing agent in this reaction. Next, they react with ammonia and bromine. So these carbides, they also react with ammonia to form these compounds liberating hydrogen gas, and they react with bromine to form calcium bromide, and this is another compound of carbon with bromine. Next, let us see this aluminum carbide. It is pale yellow colored hard crystalline substance. Pale yellow colored hard crystalline substance, and its melting point is 2200 degrees centigrade, and it is decomposed by water liberating methane, we said. Because of that reason only, this aluminum carbide is also known as methanite, and it reacts with nitrogen at about the 1800 degrees centigrade to form aluminium, to form this compound, which has aluminium 5 atoms, that is Al5C3N, and with oxygen it forms alumina, that is aluminium oxide Al2O3. Here we can see Al4C3, Al4C3, that is aluminium carbide. With oxygen it forms its oxide, that is Al2O3. And next, let's consider covalent carbides. Covalent carbides. Here, the best example for covalent carbide is the silicon carbide, that is SiC, and another one is boron carbide, B4C. Another one is boron carbide, that is B4C. And these are not decomposed at very high temperatures because of their hardness. They are used in cutting, and they are also used as abrasives. Boron and silicon carbides, they may be prepared by reducing the oxides with carbon in an electric furnace. The oxides are reduced with carbon, then boron carbide and silicon carbide, that is silica SiO2 when it is reduced with carbon. Similarly, this boron oxide, when it is reduced with carbon in an electric furnace, that is high temperature is required, then we get such type of carbides produced. Next, third type of the carbides, that is metallic or interstitial carbides. Metallic or interstitial carbides. These metallic or interstitial carbides, they are chemically inert and extremely hard like diamond. They possess metallic luster, high electrical conductivity, and are therefore called metallic carbides. And interstitial carbides, metallic or interstitial carbides are formed by the transition metals, that is D block elements, and transition metals of the periodic table. Uh, the groups are fourth B, fifth B, and sixth B groups. And here they are of they have the two types of the formulae, MC and M2C, where M is metal, that is transition metal. Here M2C type also. So Here, yam is YMC type, where yam is titanium, zirconium, hafnium, vanadium, niobium, tantalum, molybdenum, tungsten, etc. And in the case of YM2C, the yam, that is metal, stands for vanadium, molybdenum, tungsten. Next, these metals. Let's consider chromium, iron, nickel, cobalt. That was a smaller atomic radii, and therefore they do not form interstitial carbides. Although carbides of these elements are similar to interstitial carbides, yet they are distinguished from the latter by their ready reactions with water and dilute acids to give either simple hydrocarbons or mixture of methane. These elements, they also produce carbides, but they are not compared with interstitial carbides, research. And ethylene, here in the case of methylene and ethylene, like this, they produce hydrocarbons on reaction with water or dilute acids, whereas other interstitial carbides, they do not. And the carbides are thus intermediate between ionic and typical interstitial carbides. These carbides are carbides of these elements are in between ionic and typical interstitial carbides. These carbides, they have the structures having carbon chains running through much distorted metal lattices. They are prepared by heating powdered metal to a high temperature. This metal powder to a high temperature, that is around 2200 degrees centigrade, directly with carbon. Then these metal carbides are produced. Okay, next. Let's see the preparation of these carbides by heating metal with carbon. Metals like lithium and silver directly they combine with carbon, and when heated to high temperatures, here we can see the reaction: lithium with carbon and silver with carbon. So metallic carbides preparation. Next one, by heating oxides of metals with coke. Coke is one of the amorphous allotropes of carbon. So large number of carbides, example of like this second group calcium, third group boron, barium, second group silicon, fourth group aluminum, third group these elements, they may be they may react with the oxides of these elements, they react with the coke to form carbides. Here we can see calcium oxide, coke, CaC2. Here Al2O3, coke, Al4C3, SiO2 plus C. This is SiC. SiC. That is silicon carbide. This is covalent carbide, whereas these are ionic or electrovalent carbides. Ionic or electrovalent carbides. Next. See the structure of carbides chemically. The refractory carbides are solid phases rather than individual molecular species with the atoms held together by chemical bonds. That is, here these are the interstitial carbides. In interstitial carbides, where interstitial are metallic carbides. These interstitial are metallic carbides. Here, what is the present? We can see here. So metal atoms and carbon atoms are present like this. This is about the structure of interstitial carbides. Now let's see the properties of carbides. These carbides are extremely hard, and see some approaching to diamond in hardness. That is, diamond is the hardest substance we know, and here these carbides are also have certain characteristic like that of diamond in hardness, and they have high melting points also, and these are having high electrical conductivity, and many of them show this chemical inertness even under drastic conditions, as they are very stable and strong bonds they have. And the carbides are mostly likely to get attacked by oxidizing agents. Molybdenum and tungsten carbides are somewhat more reactive chemically than the metals for which they are derived, but the other carbides are somewhat less reactive than the parent metals. So when compared to metals, the carbides are more reactive with it. Next, the extreme hardness, very high melting point. We know usually it is between 3000 to 4000 degrees centigrade, and the chemical inertness of carbides render the refractory carbides of considerable importance, especially for making tools. Next, silicon carbide being used as an abrasive and deoxidant in the metallurgy and as resistors for electric furnaces. This is the use of silicon carbide, and carbides they have been used as reducing agents in metallurgy and in electrothermal work. Next, aluminium carbide is used for the preparation of methane viscid because it is a methanide, whereas calcium carbide is used for the preparation of acetylene as it is an acetylide. And the carbides can withstand high temperature. They are widely used in furnace lining because of their tendency to withstand very high temperatures. Okay, thank you. We will continue the rest of the topic in the next video. Thank you very much.